me the opportunity to talk here. Well, actually, automorphism of hyperkähler manifolds is somehow the final part of my talk, so I hope to reach it. I will start more by giving some general results, which then allow you to study automorphism in the greatest possible generality. Well, so first of all, let me start with the definition which most of you will know, is that of hyperkähler manifold. But I will complement it with a couple extra things which are less known, which are hyperkähler orbifolds and hyperkähler varieties. Or, as they are more known, when hyperkähler is quite a term dealing with the smooth case, so usually it will be irreducible, holomorphic, symplectic, manifold, orbifold, or variety. So, a compact and Kahler manifold is irreducible, holomorphic, symplectic if you first ask for it to be simply connected, and then you ask that the space of its two forms is one-dimensional, and this two form is a symplectic. What changes in the orbifold case? Well, X will still be not a manifold but an orbifold, and this symplectic form, well, you cannot really define it everywhere. So this sigma X needs to be symplectic on the regular part, and in the variety case, you have again, sigma X is symplectic on the regular part, and if you take a resolution of this, so you take a resolution of singularity P from X tilde to X, and you ask that P upper star of this form is a well-defined two form. So maybe this is not at all a symplectic form of this resolution. It doesn't matter. You just ask to have a well-defined pullback of it, and this pullback needs to be a 2 form. This is somehow implicit in the orbifold definition, but it is really a requirement otherwise. So what are examples? At least one for each category. So the first one, you take X inside P5, a cubic fourfold, and let's say Y. You take f of Y inside the Grassmannian of lines P5 as the Fano scheme. So this is a smooth cubic fourfold. As the Fano scheme of lines on Y. And by a classical result of Beauville, this one is actually an hyperkähler manifold. You can see easily that the dimension is 4 as well. So this is IHS fourfold. From this one, I will construct an example of an orbifold. In a proper orbifold. So let us take a special cubic. We take lines cubic fourfold. Where Y is the zero locus of this polynomial, which I should check. So this one, this is classically studied as the Klein's name suggests. If you take only the cubic threefold defined by this coordinates and this equation, then you obtain a cubic which contains the 11 modular elliptic curve, which was the reason Klein studied it. So what do I want to do with it?
And
so on Y, there is an order 11 automorphism. which sends the coordinates to a multiple of them. It's the identity on x equals 0. Then this is just a primitive root. You can see the equation of the cubic, which was this one, is preserved under the action. So this E is well defined on Y, and of course it is a projective automorphism, so it will send a line to a line, and so this P induces order 11 automorphism of the Fano scheme of lines. So this has actually only 5 fixed points. You see this one on P5 has only 6 fixed points. One of them is not on Y. And if you take the lines between these 5 fixed points, half of them will lie inside Y and half will not. So you get 5 fixed points for this. And this preserves the symplectic form of this Fano scheme. So if you consider the quotient by this order 11 automorphism, then what you get is actually an orbifold. It inherits the symplectic form from this Fano scheme. And, well, so this is just one example of all. So it is not trivial to compute it, but I like it because the second bit number is as small as it can be. So just 3 dimensions. an example of an irreducible holomorphic symplectic variety, which I try to make it as special as possible. So take a K3 surface. Let's say general P3 of the P2. So just a very classical example of a double cover of P2. And so this K3 has an evolution given by the double cover. S2, which is the Hilbert scheme of length 2 zero-dimensional subschemes of S, which can be thought just as a block along the diagonal of the symmetric product of S. So this manifold contains the locus of points P dot of P where P is a point on the K3, and this locus of points is clearly isomorphic to the P2 you started with. So now you could do two things with the P2. So now we contract this P2 to a point and we have a map from this Hilbert scheme to a variety Z. So this symplectic. So when you're blowing down this P2, what is happening? Well, this variety will still have a symplectic form on its regular locus because we only changed what was happening on the P2. And it has a resolution of singularities, which is this one, where the two form pulls back to a two form. So this agrees with our definition of IHS variety. So this is Z is an IHS variety. And that is not Q factorial. So this is somehow one of the differences with the previous case of orbitals, where we had a Q factorial variety. how to even approach the study of automorphism, this set of varieties? Well, first, you need a theorem which is due to go on and in this case, then, if I remember correctly, many in the orbifold so H2 let X be S, then H2 of X with the integer coefficients by linear form, quadratic form Q. X such that if you take this quadratic form, the top power times constant, then what you get is the top intersection of this class. This is for all alphas in H2. And this is a real constant, called the G constant. And this takes in the other two names. So this is actually very good news because it gives this H2 some extra structure, which is the structure of a lattice. And it makes it possible to study the image of the automorphism group inside the isometry on page 2. So this is the first step in translating a geometric problem into an algebra, which usually works very well in algebra. So what are these forms in practice? take the time scheme of lines with the coefficients and its fully monomolar form as a lattice. This is the same lattice as the Hilbert scheme of 2 points. Take surface. Actually, these two are deformation invariant. This is part of the proof of Covilent-Donati that this is irreducible holomorphic symplectic. And this lattice is the same as the lattice of the K3. Direct sum, and for me, all direct sums will be also orthogonal with the quadratic form, an extra class. Of square minus 2. And twice this class is the exception of value. From sim 2 of S, well, from the Hilbert square to sim 2 of S. And this Fujiki constant is in the other example. So this decline to fourfold modulo disorder 11 automorphism and its quadratic form. You get much smaller lattice. Well, this is the intersection. And the Fujiki constant, now it's 3 times symmetry. 33. And this was again. So what is missing to start effectively studying automorphism is precisely 2 ingredients. One is reconstructing the manifold from its second cohomology. Oh, sorry. Its second cohomology and the quadratic form int, which is Verbitsky's celebrated Torelli theorem in the manifold case. And the other one is having some control on the structure of Kahler cones in this manifold, so that you can distinguish an isometry which sends a Kahler class into something else from an isometry which preserves the Kahler code. So, let X IHS is a manifold or orbital, or also variety, but let's leave it for later. So fix is L, which is isomorphic to the H2 Z coefficients. Define a mark here. Right. Right. Here. That X prime is a deformation. X and prime from H2 prime L is an isomorphism. So you just fix an extra data which is the isomorphism with the fixed lattice L. Then there exists a smooth and non-auto complex space rising marked pairs the formation of the flex. With an object and so it is possible that this notation is a bad notation, because abstractly you could have a non-deformation equivalent hypercalars with the same lattice on the H2, but no such example is known. So for now, the notation is decent. And there is a period to a period domain, omega L. So this is just the set of points, the projective space given by the lattice tensor C, such that L times N is 0 and L times N conjugate is positive. So it's an open set in a quadric. And what's the period method? You take a point and you send it to the class of a well-defined line given by the symplectic, which by the Hodge-Riemann relation satisfies also these two extra equations. So it's always good to have a period domain. So the theorem with different names and different set here. Verbitsky in the smooth case. We have Mene in the orbital case. And we have Bakker-Lane then Young in the variety. In this setting, there are some extra hypotheses, and the situation is not exactly as I told you, especially what changes is the correct notion of deformation you should take. So, let L0 be a connected component. Then E is generically injective. So it means that up to limiting to a single connected component, you can recover more or less your manifold from its Hodge structure. So this genericity is an extra hypothesis, and 2 points the same number are given by birational or orbitals or so what gives the non-injectivity is quite clear, but still you maintain the same birational class. So we're closer and closer to automorphism. With just one extra notion. And isometry. Which of some other entity is a parallel transport. This is somehow a tautological definition. You need to obtain it by parallel transport between some deformation of x into y. So somehow with this tautological definition, you see that in this connected component, you are changing the manifold with something which is deformation equivalent to it. And the marking is changing, but of course, this change of marking is given somehow by parallel transport if you stay in the same connected components. So this notion is somehow useful to count components and to decide if two marked points are the same. If y equal to x, this is called another number. And the group number is called 1, 2 of x. So from this Torelli theorem, Verbitsky, you get a special version of it, which is somehow more precise on automorphism and birationalities. This one is somehow called the Hodge theorem. Was proved by Markman. So I'll state it in a simpler version. I take two marked points. Belonging to the same, well, with the same manifold. then they are in the same connected component. And meanwhile, even though this isometry of H2 is non-monopolar. And moreover, an element in this monodromy group is in the image of the natural map from automorphisms to isometries. Even though if there exists a Kahler class such that phi of omega is a Kahler class. So now the study of automorphisms can somehow be reduced in 3 steps. The first one, well, we need this P to be an element of the monodromy group. So we need to get our hands on this group. Otherwise, we can do nothing. Second, well, this map is clearly well defined, but it could have a cavity. So one needs also to study this cavity, so that at some point you can hope to leave an isometry to an automorphism. And then the final one is this statement. So to use it, we need to understand how the Kahler cone is shaped. Otherwise, we cannot see what are isometries which preserve it. So first, let me start with this color. So these two steps. So first of all, we have the mount to X is a deformation environment. So it somehow only depends on topological data. And second of all, also the kernel is map is a deformation environment and is finite. So all issues represented by this kernel will only be just a matter of finite group theory. So in practice, we can solve them. And so there are two deformation classes you know. Just manifolds. I can write or I'll start with the more sporadic ones, which are O'Grady's 6 volts and O'Grady's Manifolds. So this gives one deformation class in dimension 6 and one in dimension 10. Here we have E2 equals to 8, E2 4. Then we have Hilbert schemes like A3 was 23. And this at dimension 12. So this is at least infinitely many deformation classes. And here there are Kummer manifolds. And A, this can be defined as the kernel of the natural summation map from an Hilbert scheme over n+1 points on an abelian surface, where you take the n+1 points and you just sum them. And this at B2 equals 7. So the numbers at the extremes are manifolds constructed from K3 surfaces, while the numbers in between are manifolds constructed from abelian surfaces. Complex story. So in all these cases in the list, the monodromy group and the kernel of this representation is known. So the results are by various people. In case 1, the monodromy is Markman. In case 2, it is myself, but using fundamental results of Markman and Yoshioka. For grade 6 fold, it's again myself and Rapanetta. And for the grade is 10 fold, it is monographic. On 2x is known, and is maximum if x is either monogradient or inverse scheme points over Q3 when n minus 1 is a prime power. So this, of course, the result is much more precise. It tells you what this monodromy group is also in the other cases, but it will be a finite index of the maximal group. And what does this maximality mean? Monodromy serves the orientation of the cone classes. So this monodromy group needs to preserve this orientation of this cone. So as an example, minus the identity is never in the monodromy group. And the monodromy group is contained in this index 2 subgroup. And what about the kernels? Well, for either scheme, that's the wheel, or generalized inverse that's all given. And for both the already examples, that's me and bundle. So this kernel is trivial for KPMs and already manifolds. A bigger group built up by evolutions for always 6-fold. And an even bigger group, well, it depends. For generalized cumulus. So this arises by the -1 involution on the William surface and points of n+1 torsion in the William variety. And this one arises as points of 2 torsions, but not in the William variety. Sorry, not in the William surface, but in the William surface times its dual modulo ±1. So these kernels also have a geometric description. So the first issue when speaking of automorphism, given by the kernel of the representation and the structure of the group we need to consider, this monodromy group, is solved in all known cases. So what remains to deal with is the harder problem, but before going into it, let me give you a class of examples, let's say, where this problem can be completely circumvented and you can just go straight to some result. So somehow automorphism of hyperkähler manifolds can be divided in 2 realms, the realm of symplectic ones and the realm of non-symplectic ones. So some automorphism C symplectic. C upper star. of the symplectic form is again the symplectic form, and non-symplectic otherwise and also this C is purely non-symplectic, or non-trivial powers are non-symplectic. So somehow its action on this symplectic form, if that's finite order, has the same order as the original form C. So the remark if C is purely non-symplectic, and the pair C very general, then C preserves the Nerone-Severi of X. So, what do I mean with this very generality here? I mean, you just take any pair X with a purely non-symplectic automorphism, and you take deformations preserving the C action. So you just take inside H1 of the tangent, you take C invariant. Well, actually C. Well, you take one eigenspace that's the action of C, and you move in those directions, and you take a very general one. In this very general one, the Nerone-Severi will have only the minimal amount of classes, and this minimal amount is precisely those preserved by C. What is that? So that's an old result by Mouille, which is basically an adaptation to higher dimension of the work of Nikulin on K3 surfaces. That tip side U lines side invariant classes. And as psi B. Then symplectic, purely symplectic. We have that if psi contains the transcendental lattice of X, so the smallest lattice whose complexification contains H20 and H02, and dually its orthogonal is contained in the neuron. And here, the invariant part is given by algebra classes, and this contains the transcendental. So the very generality assumption is precisely that here we have an inequality. You take just a deformation where you remove every extra algebra. Here hypothesis C of finite order. So in particular, if it has finite order, you can always find an invariant Kahler class just by taking any Kahler class and doing the average over the group action. So this tells you in particular that this neuron severi contains an ample class. So this implies also that X is equal. So what do we do with this preservation of the neuron severi? Well, you can actually just look at possible neuron severi lattices with an action of some isometry on their orthogonal, which is the identity on themselves. The idea is to study non-symmetric purely. Finite order. Yes. S. T. Such that the direct sum is contained in H2 X. and this is a finite index. T as signature 1 something as signature. So what's left? So v2 of x first, yeah, very much. So that at least their sum can be a complement, and s see, which extend so basically, I'm saying that there is some isometry action on this S, which then can be extended here. And if you take invariant classes in here, you end up with T. So why this is the solution? It's almost the solution. You need to require that this is a monotony element. For any such pair, this is by subjectivity of there exists a manifold then the formation of X such that the velocity of that is isomorphic to T, the transcendental of that is isomorphic to S. I know the choice of letters seems really the bad one, but T was born with the symplectic realm in mind, so everything will be odd. And this also that is projective. This projectivity. And this C, which now is still a monodromy operator. Well, this preserves the Néron-Severi. The manifold is projective, so it preserves an outer class. So this lies in the image. Out there, inside the module. So you can actually lift it to an automorphism. And every purely non-symplectic automorphism can be studied in this way. So regardless of the structure of the Kahler or Ample form, in the purely non-symplectic, you can make your day and study everything which you would possibly want to study. So this idea is particularly nice when this C has order 2. Because one of the things which you needed was that this lattice S had an action by an isometry of this given order. And when the action, when the order is exactly 2, this action is just minus the identity. So you needed to check one thing less. You only need to find pairs S and T with the right signatures and with an extension giving you the second cohomology. So, sorry, are there questions? Okay. So what to do more generally? Well, it turns out that one extra analogy with K3 surfaces is true. If you think at K3 surfaces, well, you can draw your cone of positive classes and taking a section of it. Then you can look for the Kahler cone in this round cone. Well, what you have to do is to look for some algebraic classes, which are classes of -2 curves. And then you cut this cone with the orthogonal to these classes. So you get some maybe too simplistic drawing, but you will have components in this cone after you remove these walls. And these components are characterized by their intersection with the -2 classes. There will be one component where the intersection is positive with all effective -2 classes in this drawing that's the Kahler cone. So for K3 surfaces, it's easy to prove that -2 classes are what you need to cut out. That's just by Riemann-Roch, basically. But the thing to keep in mind is that there is a deformation invariant set of classes, you remove from the positive cone the orthogonal, you get a wall and chamber. Well, if you remove walls, you get just a chamber decomposition, and one chamber is the Kahler cone. So it becomes a combinatorial game. Well, that's the case also for hyperkellers. Only the classes which you have to remove are more, let's say. So, a wall divisor or MDN plus. So these two names give you a different flavor of the thing which I'm about to define. This is a combinatorial flavor. This will be precisely the divisors giving you the walls in this decomposition. And this is a more geometric one because this stands for monodromy birationally minimal. So these are classes which up to birational equivalence and somehow up to monodromy are obtained by minimal classes. So this is a divisor. Satisfying two conditions. The first one is that the square of B is negative. So you want to cut the positive cone, and if you want to cut it somewhere meaningful, then this square needs to be negative. And second, for all elements in the monodromy group of X intersected with the group of Hodge isometries of H2 of X, we have that F of B orthogonal intersected with the cone which I'm about to define this is empty. Be careful. This is the union over all F over all phi from X to X prime with X prime still reducible over X symplectic. You take the pullback of the Kahler cones. So you might have several birational models of this manifold. You take all the minimal ones, so those which are staying hyperkellers, and you pull back Kahler classes. You get a new cone, the birational Kahler cone, which is still contained in this positive cone. But if you have more than one birational model, this cone is not connected. And what you are requiring is that even if you change your D with something monodromy and Hodge equivalent to it, then you never meet the birational Kahler cone. If you go again down to the K3 example, that's also a suitable definition for -2 curves. If you take a monodromy operator, which is a Hodge isometry, well, this is given just by reflection along -2 curves or automorphisms. Well, semi-direct product of these two. And indeed, reflection by -2 curves just move one chamber into the other. And they shift the walls, but they don't move a wall outside of it. So these are good. And automorphism, well, they fix this component and somehow exchange the walls. So also these -2 curves are wall divisors in the K3 setting. So why are these meaningful? Well, because they are once again a deformation invariant. So I have to put many names in here. No, let me go alphabetically. One side by Hinkel on another side, and myself on the third side. This in the smooth case, and unit and the risk orbitals. And the result is that all divisors are in some sense deformation invariants. Meaning D X is a wall divisor. And f of B inside H2 of another manifold is given by parallel transfer. And you ask that this f of B is in the Ron-Severi of Y, then it is a whole divisor on one. So in this sense, they are deformation invariant. So one would try to somehow classify their orbits and see what are possible orthogonals inside the positive cone, giving you the shape of the Kahler cone. This can be done in practice, but let me mention an interesting side result of the deformation invariance. So this is a result by Kahler and Mongardi, which was proven in a series of papers, removing one hypothesis at a time until now it's hypothesis. Well, it probably has the hypothesis it needs to have. Let D a primitive whole divisor on X. Then there exists N, some natural number, such that this depends on the information. So it's somehow a constant of the deformation class, such that Q of D is bounded by this number. So you have these whole divisors are deformation invariant, and in particular they are invariant by the monodromy protection, which is a subgroup of finite index of the isometry group. And you're looking at a lattice, you're looking at elements with square which is bounded between 0 and some negative number. So their isometry orbits are also a bounded number. So a fortiori also their monodromy orbit will be bounded. And this has very nice consequences. So this is a much more recent result by Jasinski and Kurnosov, which I spelled correctly. Okay. So this allows to prove that out of X is so this kind of group is quite technical, but the point is that they are very well studied, So with their proof, automorphism of hyperkähler manifolds immediately inherit a lot of properties like finite generation and many more. But I guess Igor could be more precise in this. And how does this come from this one? Well, this is basically the fundamental step, this boundedness, in proving the Kawamata-Morrison-Kuhn conjecture for hyperkähler manifolds. And once you have the boundedness, you have the ample cone as a structure of a rational polyhedral domain times the action of the automorphism group. And that's what they use to prove that it is in this class of groups. So, to finish, let me sum up one result which can be proven at least in one deformation class. With this, you take X, the deformation equivalent, the Hilbert scheme of endpoints on a K3 surface. So here, sometimes the monodromy group was maximal, depending on n, but the kernel of the map from automorphism to isometries is always trivial. So that G inside of X be automorphism. So I'm dealing with the other realm, but only finite order, this result. Then G embeds in a fixed group, even if a huge group. So this is Conway's first sporadic group. Which is really huge. And SG, so the part where the action was non-trivial, the orthogonal to the stabilizer, is determined by the action G on the Lich lines. So this is the unique even what is 24 without, so for me it will be negative definite. Usually it's positive definite. Without minus 3 plus. So this is somehow a full classification because you can look at this lattice. Its automorphism group is an extension by minus the identity of Conway's group. And you can classify fully all conjugacy classes of a given group G. You can look at this coinvariant lattice, and you can try to embed it inside the H2 of this manifold. If you can, then your group will more or less be on the list of possible automorphism groups. If you cannot, it will not be. So this you can do completely with a computer.
Giovanni, can I ask a question about this theorem? So, suppose that n equals 1, so that you have an actual K3 surface.
Yes.
Then the answer is like more restricted, right? You have some Mathieu group instead of Conway group.
Yes, indeed.
So some phenomenon happens starting from n equal 2 and for all possible n. And can you explain maybe the idea of this change? Why n equal 1 is so much different from?
Yes. So the point is, okay, so of course, what Kostya was saying, we have this group which contains the Mathieu group on 23 elements. And for K3 surfaces, there's a result by Mukai saying that G is inside this Mathieu group. And if you look at Kondo's proof of this result, you have something similar to this statement, but then he doesn't consider Ricci lattices, but he considers all Niemeyer lattices, so all the unimodular lattices of rank 24. He actually wants to exclude the Ricci lattice to have a smaller automorphism group. So, what's the difference?
Giovanni?
Yes?
Could I ask you though, how about the Geoffrey Mason? I think he classified all these groups.
Sorry?
Geoffrey Mason, I think he classified all these groups.
That's the point, yes. So, I proved this statement, but Cohen and Mason, so they classified G actions on the Ricci lattice. So they were rough and explicit. They really look at all possible subgroups of the Conway group, all possible stabilizers, and their orthogonals. So you have a complete...
Are they able to say which groups are realized for which n?
They didn't do this, I think. There are some groups which are realized for every n, and a few groups which are not for every n.
And at least what's the qualitative behavior? You have a finite collection of groups.
Yes.
Finite number of finite subgroups inside this Conway group, and some of them are forbidden. And then suppose that I make n large enough.
Okay.
Is it true that every group from this finite collection of possible subgroups is realized for large N?
So you have an additional condition, which is that you need to have that the rank of this SG needs to be bounded. So this needs to be at most 20. So you look at groups which have satisfying this, and you want to ask if you are asking if there is some n where, or at least if from some point onward they are all realized.
Well, maybe there are other restrictions, I would guess, but
yes.
So is it true that for large N, all the groups that are possible for some N are realized for N equal to 1000?
Ah, you ask if there's a... So all of the groups are realized for infinitely many N, but I've never checked if there's a number which can be used, if there is an N which can be used to represent all of them. I don't know this.
Mm-hmm. I see.
And also you have you have more conditions than just the rank. But let me sketch what is the difference with the K2 case. So here we have the secondary number, which is 23, and here the secondary number, which is 22. So here we have this part. So this is a negative definite lattice. This can be only of rank at most 20. And here the rank of SG can be at most 19. So this already is one of the important differences for the difference in groups. But
yeah, I see.
The most important one is the other one. So here you have the SG is of course contained in H2 of X, which in turn is contained in the so-called multi-lattice, which is 4 copies of U and 2 copies of EA, the negative EA. So here you only have this, and you cannot say much more than this, but here you have the SG embeds in H2 of the ring, which again embeds in the multi-lattice. This is just the H star. And this composition tells you that SG direct sum U embeds in here. And this is precisely the trick used by, well, almost precisely the trick used by Combo, because this is SG direct sum. Well, this contains SG direct sum an elemental square minus 2. So Kondo uses this to prove that this lattice can be embedded into a negative definite rank 24 lattice, which is unimodular. And this is done using some elementary lattice theory by exploiting the fact that this can be embedded in this other unimodular lattice of rank 24. So you know that SG embeds into one of the 24 Niemeyer lattices, but now it contains a class of square minus 2. So this cannot be the Leach lattice. It's one of the other 23, which are much simpler. While here, it is really possible that the only lattice where you can embed is the Leach lattice. Let me finish you with an example of these big groups. Take a cubic, the Fermat cube. So this has plenty of automorphisms, and you consider its Fano scheme of lines. Inside it, the group of projective symplectic automorphisms So by projective, I mean those coming as projectivities of P5. This group is Z modulo 3 to the 4, semi-direct product, the alternating group on 6 elements. So you can permute all coordinates, and if you take a cube root of unity, you can multiply 3 coordinates by it, and this will give you a symplectic automorphism of order 3. Well, this group is only inside Conway group and not Mathieu group. Even if I'm asking M24. And I think I should stop here.
Okay, let's thank Giovanni for any questions. I actually have several questions. So
Okay.
first, do you have analogs? So you have a kind of classification for automorphism group of the first type of hyperkähler manifolds, and do you have similar classifications for other types?
Yes, actually yes. So for generalized Hummers, most of the work was done by myself, Kevin Tari, and Malte Wandel. But the list of groups is, at least in the finite symplectic case, that's really smaller, because the lattice you can work with is much smaller.
So you mean smaller, right?
Mm-hmm. Smaller, yes.
And do you have some beautiful group arising there, like a Conway group?
Yes, but it's less beautiful.
And what's the group?
This time is the Weil group of E8.
Weil group of E8?
Yes.
Also not so bad.
Yeah, I mean, it's one of the nice ones, yes.
And what about O'Grady's?
So O'Grady sixfold was described by my student, Annalisa Grossi. And it's only slightly bigger than this, because the lattice of the generalized Kummer and this one are strongly related. And the O'Grady.
And what's the bounding group in this case?
Sorry?
Do you also have some bounding group in this case?
No, that's, I mean, perhaps yes, but she could not find an explicit one. And
so
also,
you just have some classification, some list.
Yes. I mean, of course, everything is in the monster group. That's not satisfactory at all. And the O'Grady examples are a bit tricky, because in the symplectic case, it's difficult to find automorphism, but it's very easy to find birational morphisms. So, yeah, the results, I mean, you can do similar classification also for birational morphisms. They still define a map on second cohomology, and if you require some extra conditions, you can still work with them. But somehow it's geometrically less nice. And there's recent work by Brandhorst and Cattaneo, which are trying to get let's say, a full classification without a distinction between the symplectic realm and the purely non-symplectic realm.
And can you repeat once again? So both of the O'Grady families are served, right?
Sorry?
Both of the O'Grady families are not known from the point of view of final groups.
Not exactly. O'Grady tenfold, there's still the problem with the determination of wall divisors. So I'm working on it with Onorati. We hope to finish very soon. But until you don't know what wall divisors are precisely, you cannot classify.
And can you repeat once again, what did you say about the birational automorphism group? So you can also understand the finite subgroups there, right?
You need the extra conditions. So you usually need the action on the discriminant group of the manifold is trivial. With this condition, usually you can do a similar classification.
So it's an should be thought of as an analog of symplectic condition?
No, but this is actually, in the known cases, this is implied by not by avoiding the wall divisors in the orthogonal to the invariant lattice. So you can still have wall divisors even if you have this condition, but if you still have it, then the point is this condition ensures that when you look at this embedding here, you can extend the G action trivially outside of SG. So it's a technical condition which tells me that I can embed this SG in a nice unimodular lattice, and the action will be trivially in its orthogonal. So I can look for a nice unimodular and definite lattice where I can put all of the SGs, and then look at the groups, the automorphism group of this unimodular lattice as an ambient group for my finite symplectic automorphisms or birationalities.
And maybe one more question. So suppose that you work with the family of with the deformation family, which is the symmetric, which contains symmetric squares of K3 surfaces. So you think about fourfolds. Is it possible to distinguish the actual symmetric squares from just the deformations from on the level of finite groups, on the level of groups acting there? You have some condition which distinguishes between like actual actual symmetric squares of projective K3 surfaces and the deformations.
So you can actually find this actual Hilbert squares. It's just a condition. Well, up to birational transformation, it's just the presence of a special class inside the Ruseveri. So is this what you were looking for, more or less?
Yeah, but does this give you some restrictions? Like, is there a theorem of the following form? Suppose that you have an there exists some group, some say finite group, which can act on which cannot act on a deformation of a symmetric square of a K3 surface unless it is indeed a symmetric square itself, not just a deformation.
Ah, okay. So the restriction goes in the other way, actually.
So there are more groups acting on.
Yes, on non-Hilbert schemes. So you can. So Hilbert schemes are more or less dense in any possible sense in moduli in this family. So as soon as you can deform your pair manifold and group, so this means that the rank is at most 19, then there exists a deformation of xg of So I'm not claiming that the G action is already defined on the K. I'm just saying that this group can act on this. And actually, the problem is a little more intrinsic because you can prove so the group of this finite symplectic automorphism is actually contained in the group of possible derived equivalencies of a K3 category. So somehow the information about the K3 is always there. And you have a few cases where you cannot find it geometrically like this. And you see that these cases have rank of SG maximal, so equal to 20. The Klein's cubic and its Fanov scheme of lines was precisely one such example, where you don't have a K3 surface appearing at all.
When you don't have a K3 surface?
You don't, yes, you don't.
That's very interesting. I think it was a question of Zhenya Schindler and Sergei Galkin when they kind of related, but modulo some wrong conjecture, they related the birational geometry of a cubic to the nature of a Hilbert scheme. And maybe the crucial question was that they needed to have some actual K3 surface for rationality, and then so you mean that for a Klein cubic, its Hilbert scheme of lines is not a Hilbert, doesn't come from an actual K3 surface, right?
So yes, if I remember my computations right, yes, it does not.
Very good, very good. Okay, other questions?
Maybe I ask the question. So it's probably an unfair question because it's a question about positive characteristic. All these groups are realizing characteristic P for K3, right? Almost all groups from the Mason list, right? Yeah, because it's 4 orbits. I think this is what we classified with Perm, because this is when you have a positive characteristic K3.
But I mean, it's at least 4 orbits in the group, or
positive characteristic, it could be even 3 orbits or 4 orbits.
Okay.
So is it kind of means that just if you have characteristic P, there's no really difference between these groups. If you deform Hilbert power or just you don't deform, the list of the groups will be the same? Do you think you never probably thought about positive characteristic, right?
So I never thought about it, but yes, it's possible that actually
maybe it's the same list. I think so. It's just the
maybe you're right. I mean, maybe the elements outside of these cases can be deformed to a super singular hyperkähler manifold. Yes.
Yeah, right. So this is how these new groups appear, I think, because they just can appear characteristic P, but you don't see them in characteristic in the over complex numbers. You have to deform them, I think.
Yeah, that's quite likely, I would say, yes.
Thank you for a very nice talk.
Thanks.
Bye.
Thank you, Giovanni.